Long before there was a sun, before planets or people existed, there was only a vast cloud of gas and dust drifting through space. This cloud, known as a solar nebula, contained everything that would one day become our solar system. Every planet, moon, and asteroid we see today was once part of that original cloud. Nearly 5 billion years ago, this nebula was on the brink of transformation. It was unstable, suspended in space, waiting for something to push it over the edge. What causes a diffuse cloud of gas to collapse into solid worlds? Something must disturb the nebula, triggering the birth of stars and planets. For a long time, this question remained unanswered. Scientists have proposed two main explanations, both rooted in ancient remnants of the solar system. These remnants travel from the far reaches of space, survive a fiery descent through Earth's atmosphere, and land on our planet as meteorites. Meteorites are invaluable because they are time capsules from the earliest moments of solar system formation. They preserve a pristine chemical record from a time before Earth, before planets, before anything recognizable existed. The first solid materials formed from dust orbiting the newborn Sun. Asteroids and meteorites that formed during this period carry the chemical fingerprint of the original nebula. Some contain the oldest solid matter ever created in our solar system. When scientists analyzed a class of meteorites called chondrites, they uncovered an important clue. Within their chemistry lay evidence of a rare radioactive element known as iron-60, which can only be produced during a supernova explosion. This suggested a dramatic possibility: a nearby star may have exploded just as our solar nebula was beginning to collapse. The supernova would have blasted heavy elements into the cloud while simultaneously compressing it, triggering gravitational collapse. As the shock wave passed through the nebula, gas and dust clumped together, heating up and growing denser. At the core, our Sun was born. Around it, leftover debris collided and stuck together, slowly growing into larger bodies. Over millions of years, these growing clumps became asteroids, moons, and planets. Although the planets appear vastly different, rocky worlds, gas giants, icy giants, they all originated from the same nebula. On one small planet, the right combination of elements led to life. Every atom in our bodies was once part of that ancient cloud. While the supernova theory is compelling, it isn't universally accepted. Some meteorites tell a different story. Researchers discovered traces of another radioactive isotope, aluminum-26, which is not easily formed in supernovas. This isotope likely originated from a different source, an extremely massive and rare type of star known as a Wolf-Rayet star. These stars burn incredibly hot and eject enormous amounts of material into space through powerful stellar winds. As these winds push matter outward, they create enormous bubble-like structures in surrounding nebulae. The walls of these bubbles grow dense until gravity causes them to collapse, forming new stars. It's possible our solar system formed inside such a bubble. This would explain the abundance of aluminum-26 found in meteorites. However, the debate continues. What scientists do agree on is that our story began with the collapse of a solar nebula. One day, our Sun will also reach the end of its life, but what form that ending will take remains uncertain. Cassini's final discoveries. During its final mission, the Cassini spacecraft captured striking images of Enceladus, one of Saturn's smallest yet most intriguing moons. At first glance, Enceladus seemed insignificant, but closer inspection revealed something extraordinary. Decades earlier, Voyager data hinted that Enceladus was unusually bright and smooth, suggesting internal activity. This was surprising for a small, icy moon expected to be geologically dead. Cassini later revealed towering jets of ice and water erupting from Enceladus's surface. These geysers proved the moon was far more active than anyone had imagined. Further measurements showed Enceladus wasn't completely solid. Its motion indicated a subsurface ocean surrounding a rocky core. Despite its distance from the Sun, liquid water persisted beneath the ice. The question was, where did the heat come from? One explanation is tidal heating. As Enceladus orbits Saturn, the planet's gravity repeatedly squeezes and relaxes the Moon, generating heat. But this alone wasn't enough. A breakthrough came when scientists proposed that Enceladus's core might be composed of loose rock and gravel. As tidal forces grind these materials together, they generate additional heat, enough to sustain a global ocean. Cassini flew through the geyser plumes multiple times, sampling their contents. The spacecraft detected salt, methane, carbon dioxide, ammonia, and complex organic molecules, key ingredients for life. Later analysis revealed even larger organic compounds, raising profound questions. On Earth, life thrives around hydrothermal vents in deep oceans. Could similar environments exist beneath Enceladus's icy shell? Everything necessary for life appears to be present. Enceladus has become one of the most promising places to search for life beyond Earth. Titan and Jupiter. Cassini also transformed our understanding of Titan, Saturn's largest moon. Beneath its thick, nitrogen-rich atmosphere lies a world strikingly similar to Earth, with rivers, lakes, dunes, and weather. However, Titan's lakes are filled with liquid methane, and its sand dunes are made not of rock, but complex organic compounds. It is both familiar and alien, a frozen mirror of Earth. Meanwhile, NASA's Juno mission journeyed to Jupiter to uncover the secrets of the solar system's largest planet. After a long and perilous voyage, Juno entered Jupiter's orbit with extraordinary precision. Beneath Jupiter's turbulent clouds, liquid metallic hydrogen generates a magnetic field so vast it stretches across much of the solar system. This magnetic field traps deadly radiation capable of destroying spacecraft. To survive, Juno was heavily shielded with thick titanium armor. Even so, it follows a carefully designed orbit to minimize radiation exposure. As Juno mapped Jupiter's magnetic field, it discovered something unexpected. The field is distorted, featuring an unusual magnetic anomaly near the equator, an entirely new feature scientists had never seen before. This strange structure offers a glimpse into Jupiter's chaotic interior and reshapes our understanding of planetary magnetic fields. Rather than a traditional storm, what scientists are observing may be better described as a magnetic tempest. Deep inside Jupiter, turbulent motion could be twisting and warping the planet's magnetic field, giving rise to the Great Blue Spot and fueling the intense radiation belts that Juno must carefully navigate. Unlike Earth, Jupiter isn't a solid body. Most of the planet is made of gases and fluids moving at different speeds and depths. This constant motion makes Jupiter's magnetic field highly unstable and constantly changing. For Earth to generate a magnetic field this chaotic, our entire planet would need to be molten, something we very much hope never happens. With every orbit, Juno continues to peel back layers of mystery surrounding this giant world. And understanding Jupiter may ultimately help us understand ourselves. Many of the secrets of Earth's formation and our place in the solar system appear to be locked deep within Jupiter's massive interior. NASA's journey to Mars. If astronauts reach Mars as planned, one of the first and greatest challenges they will face is dust. Martian dust is incredibly fine and easily charged by sunlight, causing it to cling stub. Long ago, massive volcanic eruptions carved underground lava tubes beneath the Martian surface. As lava drained away, it left behind enormous hollow caverns. Because Mars has weaker gravity than Earth, these tunnels can be far larger and more stable. These lava tubes could provide natural shelters, shielding astronauts from radiation and dust storms. If sealed and pressurized, they could become ready-made habitats. However, lava tubes exist only in certain locations, limiting where settlers could live. Building artificial shelters offers greater flexibility, and robots could construct them before humans ever arrive, possibly using local Martian rock as building material through advanced printing techniques. Even with shelter, Mars remains hostile. There is no breathable atmosphere, no liquid water on the surface, and no readily available food. Although Mars is the most Earth-like planet we know, it is still far from welcoming. Mission to a comet. The Rosetta mission was designed as a journey both through space and time. Its destination was Comet 67P, a relic from the earliest days of the Solar System. Comets are ancient survivors from the Solar System's formation. Studying one up close allows scientists to open a cosmic time capsule and glimpse conditions from billions of years ago. One of the biggest mysteries Rosetta aimed to solve was the origin of Earth's water. Today, oceans cover most of our planet, but early Earth was far too hot for liquid water to survive. Evidence suggests water arrived after Earth formed, possibly delivered by icy bodies from the outer solar system. Comets, made largely of ice and dust, were long considered prime candidates. Rosetta analyzed the water vapor released by Comet 67P to compare it with Earth's oceans. Water molecules can vary slightly in composition, particularly when hydrogen atoms contain extra neutrons, forming what's known as heavy water. On Earth, there is a specific ratio of heavy water to normal water. If comet water matched that ratio, it would strongly support the idea that comets delivered Earth's oceans. Instead, Rosetta found that the comet's water contained far more heavy water than Earth's. This meant that comets like 67P could not have been the primary source of our oceans. However, this discovery didn't rule out all comets. Comets come in families, each with different compositions. Some may still carry water similar to Earth's. Rather than closing the case, Rosetta expanded it. Each answer led to new questions, pushing scientists to dig deeper into how planets, and life, formed. Rosetta also detected a rich collection of organic molecules on the comet's surface. These molecules could represent the raw ingredients needed for life, hinting that comets may have played a role not just in delivering water, but in seeding the building blocks of biology. Gravitational waves revealed. Gravitational waves were first detected in the middle of the last decade, opening an entirely new way to observe the universe. These ripples in spacetime revealed the violent collisions of black holes. Before this breakthrough, black hole mergers were purely theoretical. Now, observatories detect them regularly. So far, these detections have involved relatively small black holes, objects only a few dozen times more massive than the Sun. But the universe also contains supermassive black holes, millions or even billions of times heavier, lurking at the centers of galaxies. When galaxies collide, their central black holes should eventually merge as well. Yet no one has ever directly observed such a collision. The problem lies in energy. As supermassive black holes orbit each other, they must shed enormous amounts of orbital energy to spiral closer together. They do this by flinging nearby stars outward, but eventually, there are no stars left to eject. This creates a mystery: how do these colossal objects close the final gap and merge? The answer may lie in gravitational waves. A merger between supermassive black holes would unleash gravitational waves far more powerful than anything detected so far, waves that could finally reveal how these giants unite and reshape the universe. LIGO, however, will never hear these events. The challenge isn't sensitivity, it's time. When two supermassive black holes orbit one another, they move so slowly that a single gravitational wave can take many years to pass by. Detecting waves that stretch across decades requires an experiment that remains perfectly stable for just as long. On Earth, that level of stability is impossible. Earthquakes, weather, even passing traffic create vibrations that drown out such slow signals. LIGO simply can't listen long enough to hear them. But astronomers have found another way. Instead of using lasers, they use dead stars, specifically, pulsars. A pulsar is a type of neutron star that spins rapidly and emits a narrow beam of radiation. As it rotates, that beam sweeps across space like a lighthouse. Each time it crosses Earth, we detect a pulse. These pulses arrive with astonishing regularity. Pulsars are the most precise clocks in the universe. But when a gravitational wave passes between Earth and a pulsar, it subtly stretches and compresses space itself. That tiny distortion causes the pulsar's timing to drift, missing a beat ever so slightly. If astronomers notice that the pulse timing from a pulsar changes gradually over many years, it could be a sign that spacetime itself is shifting. By monitoring dozens of pulsars spread across the galaxy, researchers have effectively built a galaxy-sized gravitational wave detector. This technique is known as a pulsar timing array. By tracking minuscule deviations in pulse arrival times over decades, astronomers can detect gravitational waves sweeping through the Milky Way, much like a cosmic tsunami warning system. After years of observation, scientists detected the same slow timing shift across many pulsars. These stars are separated by thousands of light-years, making it nearly impossible for any local effect to influence them all in the same way. The only explanation is a shared signal passing through space itself. What they detected wasn't a single event, but something far larger, evidence of gravitational waves produced by hundreds of pairs of supermassive black holes, each at different stages of merging. Because these mergers unfold over immense timescales, countless systems are emitting waves simultaneously. Together, they create a persistent hum, a gravitational wave background filling the universe. If confirmed, this signal proves that supermassive black holes do merge after all. The ultimate goal is even more ambitious: to witness such a merger directly, detecting its gravitational waves while also pointing telescopes toward the event and watching the physics unfold in real time. Gravitational waves are revealing the hidden machinery of the cosmos. They carry information across unimaginable distances, allowing astronomers to look not just across space, but back in time. Eventually, they may let us glimpse the earliest moments of the universe itself. The birth of the universe. In the beginning, the universe erupted into existence as an incredibly hot, dense burst of energy. Space expanded rapidly and began to cool. The newborn cosmos was filled with a thick fog of tiny particles. As temperatures dropped, these particles combined to form atoms of hydrogen and helium. The fog cleared, and the first light was released, light that still fills the universe today. This ancient glow is known as the cosmic microwave background. It represents the most distant light we can observe, offering a snapshot of the universe when it was still in its infancy. But what happened before this moment remains one of the greatest mysteries in cosmology. The leading theory suggests that immediately after the Big Bang, the universe experienced an explosive growth spurt. In an unimaginably short instant, space expanded at a staggering rate. This process, known as inflation, laid the foundations for everything that followed: the structure of galaxies, clusters, and the vast cosmic web itself. The secret of the cosmic web. At first glance, the universe appears chaotic, filled with trillions of galaxies scattered across space. But beneath this apparent disorder lies an extraordinary pattern. Galaxies are not randomly distributed. They are connected in a colossal cosmic network, a web stretching across the entire observable universe. Understanding how this structure formed is one of cosmology's greatest challenges. To solve it, scientists look as far back in time as possible, studying light from the earliest galaxies. Using powerful telescopes, astronomers have detected faint strands of ancient hydrogen gas stretching across millions of light-years. These filaments are part of the cosmic web, the largest structure ever discovered. Within the dense intersections of the web lie galaxies, stars, and black holes. Along the filaments flows gas, feeding the growth of galaxies like highways connecting vast cosmic cities. This immense structure dates back to the universe's earliest days. Dark matter builds the universe. In the moments after the Big Bang, the universe was so hot and energetic that gravity couldn't pull ordinary matter together. Particles moved too fast for structures to form. But another form of matter behaved differently. Dark matter, an invisible substance making up most of the universe's matter, was unaffected by intense radiation. As the universe expanded and cooled, dark matter began to clump together. These clumps formed the universe's first gravitational scaffolding. As dark matter gathered, its gravity attracted more dark matter, building vast invisible structures. When the universe cooled enough for normal matter to slow down, hydrogen and helium gas began to fall into these dark matter wells. Over hundreds of millions of years, gas accumulated along the dark matter framework, forming the cosmic web and laying the groundwork for galaxies. Like a city built around hidden foundations, the visible universe rose upon an invisible structure. Eventually, gas collapsed into stars, galaxies ignited, and the universe lit up. A robot's guide to Mars. Decades of robotic exploration have transformed our view of Mars. Once thought to be a barren wasteland, Mars is now known to have once possessed the right conditions for life. The question is, where did the water go? NASA's MAVEN mission searches for answers by studying hydrogen escaping from Mars's atmosphere. When solar wind strikes the thin Martian air, it breaks water molecules apart, releasing hydrogen. Hydrogen comes in two forms, light and heavy. Because lighter hydrogen escapes more easily, the balance between the two reveals how much water Mars has lost over time. Surprisingly, scientists found less heavy hydrogen than expected. This suggests Mars didn't lose most of its water to space. Instead, the water may have gone underground. Water can be trapped inside rocks, bound within minerals. Geological processes can lock away enormous volumes, possibly equivalent to a global ocean hidden beneath the surface. Estimates suggest that nearly all of Mars's original water could still be there, stored deep within the planet. And Mars may be hiding water in other ways as well. Radar instruments orbiting the planet have detected signals beneath the southern polar ice, hinting at reservoirs hidden far below the surface. Mars may not be dry after all. A hidden reservoir of water may lie beneath the surface of Mars. Scientists have made an exciting discovery: a network of lakes buried under the planet's southern polar ice cap. These lakes appear to contain liquid water. They are not especially deep, likely only a few feet thick, and in some areas possibly just inches, but they stretch across wide areas. Some of them span dozens of meters and may even be linked together by shallow channels, forming something like a miniature lake system beneath the ice near Mars's south pole. This region is the coldest place on the planet, where temperatures plunge far below what liquid water should be able to withstand. So how could water remain unfrozen beneath such extreme cold? The answer may lie below the surface. As you move deeper into Mars, conditions become warmer due to heat from the planet's interior. Geological activity could be warming the ice from underneath. However, internal heat alone likely isn't enough to keep these lakes in a liquid state. That's where salt may come in. Just as salt melts ice on a frozen road, salty water freezes at much lower temperatures than fresh water. If these underground lakes are rich in salts, they could remain liquid even in Mars's brutal polar climate. Still, the evidence isn't conclusive. Some researchers suggest the signals detected could be coming from layers of frozen clay rather than liquid water. Without direct exploration, the true nature of these features remains uncertain. To settle the question, scientists would need a mission capable of drilling through the polar ice and analyzing what lies beneath. Until then, Mars's water, wherever it exists, remains largely hidden. What is clear is that the planet was once very different. In its distant past, Mars hosted vast lakes and flowing rivers. Whether those ancient waters ever supported life is one of the biggest unanswered questions, and it's one that future rovers are determined to explore.